So I'm going to introduce Eric Sonnichsen here, who has, I don't know, reams of stuff.
Oh, yeah.
Anybody that wants to read this is really welcome, but I'm sure he's going to delight us.
Well, I ought to read it to know what I'm going to say.
There you go.
Can we knock off the lights and start the projector?
Yeah.
I appreciate your interest in what we do. A lot of people who lived in Stow when I lived in Stow would drive by the factory at Packard Road and wonder what the heck was going on in that strange little building. And really what I'm here for tonight is to tell you a little bit about what went on there and what's going on now at Test Devices. We are in the business of spin testing and making spin test machines, and we have been since 1973 when we moved to Stow. I brought along a couple of show and tell objects, and you can't see it, but this is a turbine that is used to start jet engines, and in service this turbine rotates at about 60,000 RPM. The engine in your car, when you're really going fast, might make it to 4,000 RPM. So this is very fast, and every one of those little blades would like to get away. And each one of them pulls on the disc at very high force, and so the disc is working really hard to stay together. And our job is to help people understand those forces and to be sure that this thing doesn't come apart. And we'll talk a little more about it. But spin testing is simply the process of spinning this at high speed and measuring what happens. Sometimes we spin things fast enough to blow them up, and that's kind of fun. You make it, we can break it. And then catching the pieces is an interesting set of problems because they're going very fast. And this little wheel, if it were spinning horizontally and were to let go and roll to Boston, it would take it about 3 minutes. So it's going, and that's a real number, it's going really fast. Other things that we spin are things like this with lots of blades and very little disc. And then there are some other little teeny parts. Most of the parts are bigger than this, but this little dude goes at 120,000 RPM. It's used for cooling the electronics in a military application. So it's a turbine. Ed Tarnuser knows all about turbines, but mostly bigger ones. And Dick Mortensen knows all about all of this stuff because he used to be our general manager. We miss him still. Anyway, I'd like to run through the history of where we've been and how we started and what we do. Our fundamental mission, and the reason we exist, is to help customers make safer and more efficient jet engines, gas turbines, and some other interesting stuff like medical centrifuges. Medical centrifuges sit in a laboratory and they spin at these kinds of speeds, and so they're potentially quite dangerous. So part of our job is to help make sure that they don't explode and hurt somebody. Anything that rotates at high speed can, of course, come apart from centrifugal stress. The thing that we do is to spin them in very heavily armor-plated vacuum chambers to see if they burst, to measure the stress, and some other things we'll talk about. An important step in the jet engine world is to spin them at high speed and then slow them down, spin them up, slow them down, repeat for 50,000 times. And the people who have designed these parts hope that they will survive 50,000 times so that they can operate them in a working engine at about a third that number of cycles. It's not possible to make a jet engine that will last forever because you can't afford the weight of the parts that would be necessary to make them strong enough to last forever. So managing the life of these parts is quite important to our customers, and especially to those of us who climb on airplanes. There are about 1 million people every day who climb on an airplane, a commercial flight. So every day, 1 million people depend on our customers to keep them safe. So it matters. Obviously, it's a bad thing if engines blow up. It's very rare, and mostly it doesn't happen in flight. Mostly it happens with an engine that's being run up after an overhaul or something. But every once in a while, bad things occur. And as you can see, a piece of the engine disk came through the casing but didn't escape. That's very unusual. That's really good luck. And it wasn't in flight, so it just cost the engine operator about $3 million, but didn't hurt anybody. This, on the other hand, is an example of why we do what we do. This is United Flight 232. It's quite well known in our industry. It was an L-1011 where the Rolls-Royce engine in the tail section, I'm sorry, it's not an L-1011, it's a DC-10. I really am getting old. The engine in the tail section was mishandled at some point in its life, and so it exploded in flight. That destroyed all of the controls of the airplane. So they had no ailerons, they had no rudder, they had no elevator. And the pilots had to learn how to fly the plane that way in order to survive. And they did, more or less. And they, with great help from people on the ground and incredible bravery, figured out how to keep the airplane in the air and get back to Sioux City and get down on the ground. Tragically, one of the landing gear collapsed because they were going too fast. They caught a wing, and 185 people died. So why do we do what we do? Why are people careful? Because we remember that, and we don't want it to happen to anybody ever. Jet engines are actually conceptually pretty simple. They suck in outside air. They burn kerosene. Jet fuel is just kerosene, like the old lamps, but it's well refined. And then the hot gas expands through a set of turbines that drive the compressors that suck the air in. So there is a recirculating power that's going on. Fundamentally, take in outside air, heat it up, squirt it out the back at much higher speed. And that's all there is. But there are a lot of these disks with blades in them, and all of those disks would really like to blow up if you gave them a chance. So we're in the business of testing individual disks and helping people to test individual disks. It costs an engine manufacturer $100,000 an hour to run a full engine in a test cell. And each engine is worth between $3 and $5 million. So it wouldn't be good if one of the disks blew up on test. So we live because we can do it one at a time. And if it blows up, it's contained. We certainly hope. Another jet engine, a lot of high-speed disks, and a lot of things to worry about. Happily, the manufacturers worry about it a lot. And these bursts just almost never happen, and the only reason they never happen is that people are so careful. Interestingly, we're in Hudson, and a company called Pointe Tool was on Tower Street for a lot of years, and they were the primary manufacturer of a thing called a broaching machine. And Dick Mortensen's dad worked there.
I worked.
Did you? Huh.
Yeah. My old man did. I did.
Oh, my goodness. Well, to make a jet engine disc, you start with a piece of very, very high quality metal, and then you create some slots into which you insert the blades. And that, at one time, was an important industry in Hudson. So Test Devices is not the only jet engine related company for Hudson. Hudson has a very interesting industrial history. I'm a mechanical engineer. I started as a motorcycle mechanic. I stumbled into a job inadvertently at random at a company that did turbine work, and I got really interested in gas turbines and jet engines and other high-speed things. It was a kind of academic company, and they believed labor was free and materials were expensive, so they sent me off to buy a war surplus spin test machine out of the Frankfurt Arsenal in Philadelphia. And so I did that and got really interested in the business and the technology. Dorothy, my former wife, and I bought our first house in 1973 and began to try to figure out how to make a living. World headquarters, 1973 to 1981. It's that 20-foot by 20-foot single-story garage on Packard Road. You can drive by today and genuflect. We did a lot in the parking lot because there wasn't room in the building. That's proof that I was once a young guy. The pieces that we're painting there were used for a machine that we built for a Lycoming engine in Connecticut to test the gas turbine engines in the Abrams tank. The M1 tanks have jet engines in them. And when I first heard that, I thought somebody had taken leave of their senses. It turns out that because of the culture of the turbine community, jet engines are extraordinarily reliable. And they're very expensive, but they don't break. And that's really important when you're on a battlefield in a tank. The earlier tanks had a mean time to failure of 4 hours. So the gas turbine improved that. But, you know, the defense of the free world, much to the surprise of our customers, depended somewhat on a 20 by 20 foot garage in Stow, Massachusetts. We didn't like to tell them that part until later. This is a machine that we built out of that garage that is still in Norway, helping to test the parts for the cockpit air conditioner in the F-16 fighter. There was a deal between the United States and Europe for us to allow the co-production of some key parts to the F-16, and they would agree to use the F-16. So we got to make the spin test machine. And when the project manager came up from Connecticut to inspect the machine before we shipped it, he drove by Packard Road a couple of times. And we had a beam from the maple tree, and that was chained to the tree, and that was how we lifted heavy things. So he never entirely got over that. Our bigger machines back then, we'd build the peripheral stuff in Stow, and then we had a machine shop in Philadelphia who would build the heavy stuff for us. And then Ed Benedict, I don't know if anybody remembers Eddie, but he was my workforce. And we would load it all in a U-Haul truck and go to Philadelphia, put it together, run it off, and ship it from there. For a while, we made these test stands for the fuel controls on diesel engines. Our market was the U.S. Navy. A large Navy ship like a destroyer may have as many as 1,000 diesel engines on it or associated with it. And many of them have governors that need to be tested, overhauled, and calibrated. So we made those test stands. We shipped 5 of them to China back before that was a popular thing to do. 1981, my wife thought that the 20 by 20 foot garage and having employees occupy the whole bottom floor of our house and the basement was a little much. And so we ended up at 6 Loring Street in Hudson. And we were there for quite a while. It's a wonderful old building. And Hudson is a town that is compatible with and friendly to people in productive enterprise. Stow has not been so welcoming in general. Yeah, I bet you know that, don't you, Dick? Again, we needed to use the parking lot. This one went to Rolls-Royce in Indianapolis. Believe it or not, there's Rolls-Royce in Indianapolis. But we couldn't fit it through the door after it was built, so we had to build it in the parking lot and cover it with tarps at night, but that was okay. And then, through a long set of odd circumstances, I was able to acquire a surplus machine that was stored in our friend Dave Lynch's barn for several years until a customer said that we had to set it up and use it for them. So this was the beginning of our testing service. We still have that venerable thing. Now this is, some people, like to put their first dollar on the wall. This is the first part that we tested that made a difference in some people's lives. This is one of the turbines from the engine that runs the Black Hawk helicopter and the Sea King, and also some commuter airplanes. And for a bunch of reasons that are boring, General Electric decided they really needed to test it with us rather than to do it themselves. So we did, and it was approved for 10,000 cycles of operation. So we ran it, and it blew up at 2,000 cycles of operation. And there were some helicopters that already had gone that long. So there was great gnashing of teeth and concern, and they said, oh, I hope you did something wrong. So they brought another one out, and we did it again, and it blew up at 2,000 hours. And so there was even more consternation. But it established us as a good place to go, because later on we figured out what we had done right and what they should have done in Lynn. And ultimately, they shut down their test facility in Lynn. They had all kinds of problems, and they just said, you guys do it better. So we did it. 1985, another important event in my life was testing a machine that we had built, and that's the machine on the left. That's the machine on the right after we tested it. Half the lead bricks that were lining the machine came out, blew holes in the wall every 3 feet. All of the 600 pounds of the disk that we were testing escaped and went in various places. Happily, it happened about 1 in the morning. Happily, I and the 2 other people who were with me were missed. I don't know why we were missed. I really appreciate it, and I give thanks for that. But the only place where there weren't 40-pound lead bricks flying at very high velocity was right where we were standing. So we were pretty proud of what we were building up until that moment. And any vestige of arrogance was gone at that point. So now we build them stronger. We know why that happened. We know not to do what we did wrong. And we still operate all of these machines in concrete reinforced test cells. We've never had another problem like this, and we sure hope we don't. but we like to have a big concrete wall between us and things that are blowing up. The energy in the disk that blew up there is equivalent to four fully loaded 80,000-pound tractor trailers hitting a wall at 60 miles an hour. And that all happens in that little 30-inch diameter space. So we have about, well, in machines of that size, we have about 7 inches of very high-strength steel and then 4 inches of lead to cushion the blow. And it has so far proven to be enough. We only had 5 inches there, and it wasn't high strength. And what really happened was that the lead bricks got thin, and therefore they got tall, and they blew the cover off. So we fixed that problem. But it was a bad day, and there were a few minutes when I wasn't sure I wanted to be in this business ever again. Another bad day, and Kathy may remember some of this because she was helpful to us. We rented some air compressors, which we use to power the drives of these machines. And one of them caught fire, and we had them inside the barn there. And that was a bad idea. My idea, bad idea. So it took out the barn. It was a 5-alarm fire in the middle of the day. The fire extended to the end of the building. That really badly burned corner was, of course, my office. And if anybody deserved it, it was me, so it's okay. But that was really awful. That was another time when I really questioned what I'd chosen to do for a living. And there were about 30 seconds when it was all over where I just stood in the street and cried. But then I got over it. But these are the things that often mark the life of a growing business in technology. There will be surprises, there will be setbacks, there will be various kinds of disasters. I had a financial disaster once when we built a very, very expensive machine for a customer in Yugoslavia, and then Yugoslavia disappeared as a country. We still have that machine, but we use it. So these are the kinds of things that are endemic in the operation of a small company. And if you decide to be a mechanical engineer and take on some of this riskier stuff, you better be prepared. In 2006, we moved out of Loring Street. We had gotten too big, and it was really an unsuitable building in a variety of ways, but I still have great affection for it. It's now occupied by Bob Karras. Bob used to live on Boxborough Road, and he's a very skilled welder, and you may have seen some of the decorations on the building. He makes weldments for very expensive homes. Things like really good stair rails, and his son is a professor of metal sculpture at Northeastern, and they work on it together. So Bob now occupies that building and does it justice. We're in the building next to the Comcast location, and it used to make agricultural knives for Rexnord, and then the company went private and was bought by Lund International, and then they decided to move out and it became available. So that's where we are now. Anytime anybody wants to come visit, we'll show you through. We occupy about half of it. This is the company now, starting as Eddie and Eric. Now there are actually 30 of us, and my friends and colleagues are standing around a machine that's currently being finished for delivery to a customer in China. We're actually building them, 2 of them. It's a 54-inch capacity machine for very large power generation turbines. Again, something dear to Ed Tardner's heart. 270 years of combined experience. 65% of us are engineers, a quarter of us are skilled technicians, and about 10% administrative. Somebody's got to, ride herd on us and make sure that we keep track. We have 5 test cells. These are some of our customers, everything from AP Racing to Pratt & Whitney and General Electric, ABB in Europe, Switzerland, Honeywell. Honeywell's a customer. They make most of the small jet engines that are used on business jets. So your friend and his, Donald Trump, probably has a Honeywell engine. In addition to those customers for whom we do the spin testing, we manufacture machines for these guys. I think we're up to 45 systems worldwide. We run from 20,000 to 160,000 RPM, and we have electric drives and compressed air drives. And we survive and grow because we're dedicated to making things better all the time. That's our job. We stay ahead of the competition, even though the competition is actually our customer. Our biggest competition is people who decide they can do it themselves. So in order to run faster than they are, we have to work hard to innovate with test technology and our ability to deliver and all the things that you would think would need to happen in order for a company to survive. We have several guys with PhDs. I'm not one of them. And remember motorcycle mechanic? That's me. We do advanced analysis in predicting the stress and the deflection and all the things that can happen to something when it spins at high speed. Unfortunately, I couldn't make this work, but this is a high-speed video of a disk being intentionally burst, and you can watch it come apart. It's very helpful to our customers. It requires a very high-speed camera because it's going very quickly, and this is a still shot with a high-speed camera. It's actually one frame of a movie. That is, the movie is fast enough that you can actually watch the cracks grow and the thing come apart. And that's very helpful to people who are trying to figure out what makes them break. We do all kinds of things like measuring how much they expand at speed, because you spin anything and it gets bigger. We have unique capability to run these engine parts at the temperature that they will see in the jet engine. And that's just as hard to do as it sounds, but we have some really bright guys who know how to do that. So we can run these things at very high temperature. A new business for us that's growing rapidly is to spin these disks at a high enough speed to stretch them permanently. And we do that before they're finished. You notice that none of these disks have the blade slots, for example. So these come from a company in Worcester called Wyman Gordon, who are one of the major forging companies in the United States. We put them in our machine and we spin them at a high speed, and they groan and creak and stretch and they get more uniform and they become stronger and they last longer. So that is becoming an important production process for us. This is a typical, very large turbine disk. You notice the blades all supported there. And in this case, this is another power generation turbine. All these lights are being run by something like that, or a stack of those somewhere, maybe even Seabrook. And just another picture of that disk while a couple of our guys are looking at the instruments that we install on the disk to try to measure what happens when it spins at high speed. This is kind of an interesting issue. Because of advances in machining technology, it's now possible to build these disks and blades all as one piece. So this started out as a big lump of metal, and then everything that wasn't a blade was whittled away in a computer numerical controlled machine, not by us, but by our customer. And so the blades are a part of the metal, and there's no chance for failure of the attachment, and the attachment doesn't have to be as heavy, and there are certain operational advantages. The problem is, let's see if I can demonstrate this. Maybe. Every one of the blades acts like the wine glass that where you can sing the right note and burst the wine glass, if you're an opera singer. Every one of those blades has a slightly different frequency, but the better you make it, the closer the frequencies are. And there are things in the engine that generate that frequency. So that's called high frequency fatigue, and the blades can fall off at certain operating conditions. When we first learned about this, the Air Force logistics manager said to a meeting I was in, guys, you got to fix this. It's costing me $200 million a year. And there was no way to test. You had to run the engine, $100,000 an hour, and if a blade fell off, you lost the engine, $3 to $5 million. Don't like that. So we developed a method. We were paid by the Air Force to develop a method to excite this behavior in a spinning disk. Nobody could have done that before our guys figured it out. And that's been an important business for us. Everybody needs this testing capability. We do some of this testing, but mostly we export the machines that do this testing for the blade resonant failure, and they go to countries that are starting out in the jet engine business and trying not to have this problem. This is the biggest machine we've made. It will contain a 100-inch disc. It's 80 tons of steel, and you don't get Jeff with the machine, but he was the designer, so he got to get the picture. So that's us. It's what we do, and we love to talk about it, and would love to hear if anybody wants to talk about it, and anybody wants to come by just anytime you want. Please come. We'll walk you through, and you can see it live.
Well, thank you very much. Very good.
Thank you for your interest.